The ground beneath your feet is not as flat as it seems. An invisible cosmic sculptor is constantly warping the very fabric of space around you. This is the great tug-of-war between geometry and gravity, a fundamental battle that dictates the motion of planets and the ultimate fate of the cosmos. By the end of our journey, you will see the hidden curvature of the universe with your own mind's eye. We will uncover how a beam of starlight bending around the sun shattered 2,000 years of scientific thought. We will reveal why time itself slows down in the presence of a massive object. What does it truly feel like to live in a curved reality? For 2,000 years, Euclid's geometry was not just a mathematical system, it was reality itself. His elegant rules described a world of perfect, predictable flatness. You could draw a triangle on a piece of paper, measure its 3 angles, and they would always, without fail, add up to 180 degrees. Parallel lines like train tracks would run side by side forever, never getting closer or farther apart. This was the stage upon which humanity believed the universe played out its drama. It was a stage without hills or valleys, a perfectly rigid grid. This worldview was so deeply satisfying, so logical, that it felt less like a discovery and more like a fundamental truth. It was the geometry of common sense, but what if the stage itself was not rigid? What if it could bend and warp? This perfect, flat world was about to meet its greatest challenger, a force so pervasive we barely notice it: gravity. Isaac Newton watched an apple fall and saw a straight line. To him, gravity was an invisible, instantaneous pull, a mysterious force reaching across the void to tug the moon towards the earth and the apple towards the ground. His mathematical laws were a triumph of human intellect, predicting the motions of the heavens with breathtaking precision. Yet this power came with a profound puzzle. How could the sun, 93 million miles away, exert a force on our planet without anything in between? How does gravity bridge the emptiness? Newton himself was deeply unsettled by this notion of action at a distance. He called it so great an absurdity that no thinking person could ever fall into it. His own theory contained a ghost, a silent command transmitted through nothingness. The universe, in his view, remained a passive stage, the flat and rigid grid of Euclid's geometry. On this stage, planets and apples were merely actors, pushed and pulled by unseen strings. The stage itself did not bend or warp. The geometry of space and the force of gravity remained 2 separate characters in the cosmic play, one a static setting and the other a mysterious actor. This separation, this unanswered how, left the door wide open for a new performer to step into the light and change the entire production. Einstein dared to ask what would happen if the stage itself was alive. He envisioned the universe not as a static grid, but as a vast, flexible fabric, a single entity he called spacetime. This was not just space, the empty container we move through, but a 4-dimensional weave that included time itself. In this radical new picture, the sun does not reach out with an invisible hand to pull the Earth. Instead, the immense mass of the sun creates a deep, cosmic dimple in this fabric of spacetime. The Earth is not being pulled, it is simply rolling along the contours of this curvature, like a marble tracing a groove on a gently sloping surface. This natural path, the straightest possible line through a curved geometry, is known as a geodesic. With this single idea, Einstein merged the actor with the stage. Gravity was no longer a mysterious force, it was the very architecture of the universe. The tug-of-war between geometry and gravity reached a fever pitch. The elegant, flat rules of Euclid, which had stood for millennia, were suddenly inadequate. they could not describe the warped paths of planets or the bent journey of light. A new and more powerful geometry was needed to map this curved reality, a mathematics that could see the invisible hills and valleys of the cosmos. Einstein's happiest thought arrived like a quiet revolution. He pictured a person inside a freely falling elevator, feeling completely weightless. In that moment, there would be no experiment, no sensation, that could tell them whether they were falling in a gravitational field or simply floating in the empty, gravity-free depths of deep space. This simple yet profound idea is the equivalence principle, and it became the master key that unlocked his theory of general relativity. It declared that gravity and acceleration are, in essence, the same phenomenon experienced from different points of view. If you are in a rocket ship accelerating steadily through space and you shine a beam of light across the cabin, the floor is rushing upward to meet the light. From your perspective inside the ship, the light beam would appear to curve downward. But if acceleration can bend light, and acceleration is equivalent to gravity, then gravity itself must also bend light. This single thought experiment shattered the oldest rule in the book. Light, the very symbol of straightness and constancy, does not travel in a straight line when it passes near a massive object. It follows the curves of spacetime. The war between geometry and gravity had just escalated dramatically. It was no longer just about the orbits of planets. The battlefield now included the path of every photon in the universe and the very flow of time itself. The rigid ruler of Euclid was being replaced by a flexible measuring tape, and the first person to seriously test its limits was the mathematical genius Carl Friedrich Gauss. In the early 19th century, he conducted a bold experiment, surveying a giant triangle formed by three distant mountain peaks. He meticulously measured the angles between these points, and if the world were truly flat as Euclid described, those three angles would have summed perfectly to 180 degrees. They did not. The discrepancy was tiny, but it was there, a silent testament to the fact that he was not drawing on a flat sheet of paper, but on the curved surface of a planet. This was the first concrete evidence that our reality requires a different kind of mathematics. Gauss had begun to chart the invisible hills and valleys of space itself, but it was his brilliant student, Bernhard Riemann, who would hand Einstein the keys to the cosmos. Riemann imagined spaces that were not just gently curved like a sphere, but wildly, complexly warped in multiple dimensions, spaces where the very concept of a straight line had to be completely redefined. He developed a comprehensive new geometry, a language built on intricate objects called tensors. Think of a tensor not as a single number, but as a sophisticated data structure, a multi-layered description that can capture all the stretching, squeezing, and twisting of a geometric space at any single point. This was the essential toolkit Einstein needed. Without Riemann's mathematics, the beautiful idea of a flexible, four-dimensional spacetime would have remained a philosopher's daydream, a concept without a formula. Riemann provided the grammar and the vocabulary to write the laws of physics onto a curved universe. In this new geometric reality, the old, comfortable rules are broken. Draw a triangle on the surface of a sphere with one corner at the North Pole and the other two on the equator. The lines you draw are the straightest possible paths, the geodesics, but they are arcs of great circles. When you add up the three angles of this triangle, you will get more than 180 degrees. Similarly, take two lines starting at the equator and heading due north. They seem parallel, both aimed at the pole, yet they will inevitably meet. The geometry of our world is not a global flatness with local bumps. It is a fundamental curvature that rewrites the very definition of shape and distance. Euclid's geometry is not wrong. It is simply a local special case, a simplified rulebook that works on your desk but fails catastrophically when applied to the cosmos. This was the profound shift, the moment mathematics caught up with the universe's true, flexible nature, providing the precise language to describe the very curvature your mind is now learning to see. The most famous picture of gravity is a stretched rubber sheet. Place a heavy bowling ball in its center, and it sinks into a deep, smooth depression. Now roll a marble across the stretched fabric. Instead of flying off in a straight line, it curves, spiraling around the central mass in a graceful orbit. This powerful image gives you an immediate, gut-level understanding of how our solar system works. The sun's mass warps the cosmic fabric, and Earth follows the resulting curve, a celestial marble in an endless groove. It is a beautiful and deeply intuitive analogy, a first glimpse into the mind-bending reality of curved spacetime. But this picture, for all its clarity, is also a lie. A necessary and useful lie, but a lie nonetheless. The rubber sheet model contains a hidden flaw, a circular logic that can trap your understanding if you are not careful. Why does the bowling ball create a dip? It falls downward because of gravity, the very force the model is trying to explain. We are using gravity to explain gravity, a cosmic tautology that leaves the true nature of the warp a mystery. Furthermore, the sheet shows only a two-dimensional curvature, a simple dip you can see with your eyes. General relativity, however, describes a curvature woven through 4 dimensions, 3 of space and 1 of time. The rubber sheet shows you the spatial valley the Earth moves through, but it cannot show you how the sun's mass also creates a temporal slope, a gravity well where time itself flows more slowly at the bottom. So why do we cling to this imperfect picture? Because it is a starting point. It gives your mind its first foothold in a landscape where straight lines are an illusion. It is a training wheel for your intuition, preparing you to let go of the sheet and finally see the full, 4-dimensional shape of the universe. The rubber sheet is a beautiful lie, but in 1919, a team of astronomers set out to find the truth. Arthur Eddington led a daring expedition to the remote island of Principe, off the coast of Africa. His mission was audacious, to use a total solar eclipse as a cosmic magnifying glass. Einstein's new theory made a precise and startling prediction. As light from distant stars traveled near the sun, it would not journey in a straight line. The star's mass would warp the spacetime around it, forcing the starlight to follow a curved path, a geodesic through bent geometry. From our vantage point on Earth, this would make those stars appear slightly shifted from their known positions in the night sky. The only time this shift could be measured was during the brief, eerie darkness of a total eclipse, when the moon perfectly blocked the sun's blinding face, revealing the stars right beside it. The expedition was a race against weather, war, and clockwork precision. On the day of the eclipse, clouds threatened to ruin everything, but in the final moments of totality, the skies cleared just enough. Eddington and his team took a series of photographic plates, capturing the ghostly corona and the displaced stars. Back in his laboratory, he measured the tiny deflections in the starlight. The results matched Einstein's predictions almost exactly. A beam of light had bent, the universe had curved. This was not a subtle mathematical argument, it was a direct, observable fact. The news exploded across the globe, catapulting Einstein to instant fame. The Newtonian universe, with its passive stage and mysterious forces, had been irrevocably shattered. Eddington had not just confirmed a theory, he had handed humanity a new pair of eyes. We could finally see that space is not a static container, but an active, dynamic fabric that shapes everything within it. The cosmic dance had a visible stage at last. Eddington's Eclipse experiment was just the beginning, a small crack in the door to a new reality. Today, our most powerful telescopes have swung that door wide open, revealing a universe where gravity sculpts light itself. Gaze into the Hubble Space Telescope's deep field images, and you will find something astonishing. Nestled among countless points of light are galaxies stretched into shimmering arcs, delicate rings, and multiple, ghostly copies of themselves. These are not camera glitches or artistic renderings. This is gravitational lensing, a direct and spectacular glimpse of spacetime's curvature written in light. The phenomenon works exactly as Einstein predicted. A massive galaxy cluster containing trillions of stars and vast clouds of dark matter sits between us and even more distant galaxies. The immense gravity of this foreground cluster warps the fabric of spacetime around it, creating a colossal cosmic lens. As the light from the background galaxies travels through this warped region, it does not move in a straight line. It follows the curves, bending around the cluster and converging toward our telescopes. The result is a natural magnifying glass, one that can distort, brighten, and even multiply the image of a single, faraway object. This is not just a beautiful cosmic illusion, it is a fundamental tool for modern astronomy. By analyzing these distorted arcs, scientists can perform a kind of cosmic cartography. They can map the invisible distribution of dark matter within the lensing cluster, matter that emits no light but whose gravitational pull is the primary architect of the lens. They can also use this natural magnification to peer further back in time than ever before, spotting faint, infant galaxies from the universe's earliest epochs. In some cases, the lensing effect is so precise that it can even reveal individual exoplanets orbiting stars in those distant galaxies. Every one of those stretched arcs is a signature, a visible testimony that the space through which light travels is not empty and flat, but is dynamically shaped by mass and energy. You are not looking at a simulation or an artist's concept. You are looking at a photograph of curved geometry. You are seeing with your own eyes the invisible hand of gravity tracing its influence across the sky. This cosmic lensing shows us the grand architecture of curved space, but its deepest implications are written into the motion of our own planet. We watch the Earth sweep around the Sun year after year, a perfect, predictable ellipse. For centuries, we believed this was a dance of forces, a constant tug-of-war. The Sun's gravity pulls the Earth inward, while the planet's own forward momentum tries to carry it away in a straight line. The orbit is the elegant compromise between these two opposing tendencies, a perpetual fall that forever misses the ground. It is a beautiful explanation, but it rests on a ghost, that mysterious, invisible pull acting across millions of miles of empty space. Einstein's universe offers a radically different and far more elegant picture. In this view, there is no pull at all. The immense mass of the Sun does not emit a force, it sculpts a shape. It presses down into the fabric of spacetime, carving a deep, four-dimensional well. Now consider the Earth's path. It is not being forced to curve. It is doing the most natural thing possible. It is following a straight line. This might sound impossible. How can a circle be a straight line? The answer lies in the geometry of the space itself. A straight line on a flat piece of paper is obvious, but what is the straightest possible path on the curved surface of a globe? It is not a line you can draw with a ruler. It is the arc of a great circle, like the path an airplane flies between continents. This is a geodesic, the natural trajectory of an object moving through a curved landscape without any forces acting upon it. The Earth is in a state of perpetual free fall around the Sun, tracing the straightest possible route, the geodesic, through the warped geometry the Sun creates. Its elliptical orbit is not a path of compromise, it is a path of pure, unforced geometry. The planet is simply gliding along the contours of the cosmic terrain, following the invisible groove etched by mass. This single shift in perspective dissolves the mystery of action at a distance. There is no ghostly force reaching across the void. There is only the shape of the stage and the actors moving freely across its curves. The cosmic dance is not a forced performance, but a natural and inevitable glide. While the Earth glides smoothly along its geodesic, another planet tells a far more restless story. Mercury, the scorched and sun-scorched innermost world, has a small but persistent anomaly in its motion, a wobble that defied explanation for 200 years. Astronomers call this the precession of its perihelion, which is the slow, gradual shift in the point of its orbit where it comes closest to the Sun. Think of Mercury's elliptical path not as a fixed, rigid oval, but as a slowly rotating ellipse, like a hula hoop spinning around a central pole. Newton's laws of gravity could explain most of this rotation, caused by the gentle gravitational tugs from the other planets. But a tiny fraction of the wobble remained stubbornly unaccounted for, a ghost in the celestial machine. It was a small discrepancy, just 43 arcseconds per century. To put that in perspective, that is the angle a single human hair would subtend if you held it up about 1.5 miles away. It was a minuscule error, but it was real, a tiny crack in the otherwise perfect edifice of Newtonian physics. Scientists proposed all sorts of wild ideas to explain it, even suggesting the existence of an unseen planet, dubbed Vulcan, orbiting inside Mercury's path. But Vulcan was never found. The wobble remained, a silent, persistent question mark hanging in the void. When Einstein completed his equations for general relativity, he turned them toward this ancient puzzle. His theory described not just the sun's gravity well, but the specific, intense curvature of spacetime in the region immediately surrounding it. In this severely warped space, close to such a massive object, the geodesics themselves are subtly different. The straightest possible path for Mercury is not quite the same ellipse that Newton would have predicted. Einstein's calculations showed that as Mercury rolls along its geodesic through this profoundly curved geometry, its point of closest approach to the Sun should naturally drift by that exact, precise amount, 43 arcseconds per century. The math was undeniable. The moment he saw the result, Einstein felt his own heart skip a beat. This was not a prediction waiting for a future test like the bending of starlight. This was his theory reaching back through time and solving a problem that had vexed science for generations. It proved that general relativity was not merely an alternative to Newton's universe. It was a deeper, more complete description of reality. That tiny, unyielding wobble was the universe's own signature, confirming that space and time are woven into a flexible, dynamic fabric. Mercury's restless wobble was a whisper from the curved geometry of space, but the warping goes far deeper than planetary paths. It reaches into the most fundamental rhythm of the universe, the steady beat of time itself. Two identical, perfectly precise clocks are separated, one placed on the surface of our planet and the other sent to a satellite high above in the emptiness of orbit. If you could watch them both, you would witness something impossible. The clock on Earth begins to fall behind, its ticks arriving just a fraction of a second later than the ticks from the clock in space. This is not a mechanical error, it is a direct consequence of living at the bottom of a gravity well. Time itself is stretched and slowed by the presence of mass. This phenomenon, called gravitational time dilation, reveals that time is not a universal, absolute backdrop. It is a local experience woven inseparably into the fabric of spacetime, and its flow changes depending on where you are and how much gravity you feel. The stronger the gravity, the more time is stretched, the slower the clock will run. This incredible prediction of general relativity is not just a laboratory curiosity, it is a practical engineering problem solved every single second. The Global Positioning System, the GPS that guides your car and your phone, relies on a constellation of satellites, each carrying an atomic clock of breathtaking precision. These satellites orbit high above the Earth, in a region where the planet's gravitational grip is measurably weaker. From their higher perch in the cosmic terrain, their clocks naturally tick faster than identical clocks on the ground. If the satellite computers did not constantly correct for this relativistic speed-up, the entire system would fail. The positioning data it sends to your phone would drift by several miles within a single day. Your map application, then, is a silent but continuous testament to a warped reality. It is proof that gravity does not merely bend the paths of planets and light. It twists the very flow of time, binding the cosmic and the commonplace into a single, curved reality. Gravity's ultimate victory is written in the silent darkness of a black hole. This is where the cosmic tug-of-war ends and gravity wins completely. The gentle curves and slopes of spacetime around stars and planets sharpen here into an infinitely deep well, a puncture in the fabric of the cosmos. The curvature becomes so extreme that the very paths light travels, the geodesics, turn back in on themselves, trapping every photon within an unseen boundary. We call this boundary the event horizon. It is not a physical surface you could touch, but a point of no return in space itself, a one-way street leading out of our observable universe. Once an object crosses this threshold, its future is inexorably directed toward the center. Our classical understanding of geometry shatters. The elegant rules that describe triangles and parallel lines become meaningless. Even causality, the fundamental principle that cause must precede effect, begins to fray. According to renowned physicist Kip Thorne, at the very core of this collapse lies the singularity, a point where the curvature of spacetime is predicted to become infinite. Here, the density and gravity soar beyond any finite value, and the known laws of physics simply cease to apply. A black hole is not just a dense object. It is a region where matter and energy have warped the geometric landscape so profoundly that they have torn a hole in the map of reality itself. It is the most dramatic possible manifestation of the battle we have been tracing, a place where gravity does not just bend the stage, it shreds the very script of the play. The silent victory of a black hole is not always a quiet one. Sometimes it rings like a bell. Far across the cosmos, two of these gravitational monsters can find themselves locked in a final, fatal dance. Spiraling inward at nearly the speed of light, they whip the very fabric of spacetime around them into a frenzy. Their violent merger does not send out a flash of light or a shower of particles, but something far more fundamental, a ripple in the geometry of the universe itself. This is a gravitational wave. Do not think of it as a wave traveling through space, like a sound wave moving through air. This is a wave of space, a traveling distortion in the distances between things. As the wave passes through you, it would stretch your body in one direction while simultaneously squeezing it in another, an invisible, cosmic tide that subtly rewrites the dimensions of everything in its path. For a century, these waves were just a beautiful mathematical prediction of Einstein's theory, seemingly too faint to ever be detected. Then, in 2015, an experiment of almost unbelievable precision proved him right once more. The Laser Interferometer Gravitational Wave Observatory, or LIGO, recorded the specific chirp, the final spiraling whisper, of two black holes colliding over 1 billion light-years away. The instruments did not see anything, they heard it, translating the minuscule stretching and squeezing of spacetime, a distortion thousands of times smaller than an atomic nucleus, into an audible signal. That single chirp was a direct message from the warped heart of the cosmos. confirming that spacetime is not a static stage, but a dynamic, flexible entity that can vibrate, carry energy, and ring with the echoes of the most violent events imaginable. We are no longer just seeing the universe, we are now listening to its hidden geometry sing. That gentle ringing of spacetime is a whisper from the local curvature around black holes, but the cosmic fabric is also engaged in a far grander, more relentless motion. Look out at the sea of distant galaxies, and you will find a strange and consistent signature in their light. The color shifts toward the red end of the spectrum, as if the very light is tired from its long journey. For decades, the simplest explanation was that these galaxies are all rushing away from us, like fragments from a cosmic explosion. But the deeper truth is far more profound. It is not the galaxies that are moving through space, it is the space between us and them that is stretching. The very fabric of the cosmos is expanding, and the galaxies are simply being carried along for the ride. Think of the universe as a loaf of raisin bread rising in the oven. The dough itself, representing space, stretches in all directions. Each raisin, a galaxy, moves away from every other raisin not because it is traveling through the dough, but because the dough itself is expanding. This cosmic expansion is stretching the very wavelengths of light as they travel for billions of years, redshifting them into a lower energy state. This idea flows directly from the equations of general relativity, revealing a curvature of the universe on the largest imaginable scales. The overall geometry of everything, the shape of the cosmos as a whole, is not a given, it is a question. Is the universe flat, like an infinite sheet of paper where parallel lines truly never meet? Is it closed like the surface of a sphere, finite but without an edge? Or is it open, curving away from itself in a saddle-like shape? The answer is written in the total amount of matter and energy contained within the cosmos. This grand geometry dictates the ultimate fate of everything, determining whether the expansion will continue forever, slow to a halt, or eventually reverse in a great cosmic crunch. This is not a static curvature like a permanent hill, but a dynamic one, a gradual and relentless change in the very scale of the cosmic fabric over time. The tug-of-war between geometry and gravity is not a battle with a fixed outcome. It is an ongoing, evolving process, a story whose final chapter is still being written by the invisible architecture of space itself. This relentless cosmic expansion holds a secret even more startling than the stretch itself. The universe is not just growing, it is accelerating, flying apart at a pace that increases with every passing moment. This discovery arrived from the faint, dying light of exploding stars halfway across the visible cosmos. Astronomers used these supernovae as cosmic mile markers, expecting to measure how much the universe's expansion had slowed over time, braked by the collective gravity of all its matter. Instead, they found the opposite. The distant stellar explosions were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion was speeding up. Something was actively pushing the galaxies apart, overwhelming gravity's patient, attractive pull. We call this mysterious something dark energy. It acts as a kind of anti-gravity, a repulsive force woven into the empty space between galaxies. In the grand tug-of-war between geometry and gravity, dark energy is the new and dominant player on the field. Its presence directly shapes the large-scale geometry of the cosmos, forcing it toward a specific, flat, and ultimately barren fate. Imagine the cosmic fabric not as a gently stretching rubber sheet, but as a rising loaf of bread where the yeast itself is getting stronger, causing the dough to expand at an ever-increasing rate. This is not a force you can see or feel, but its effect is written into the ultimate destiny of everything. It dictates that the universe will continue to expand forever, growing colder, darker, and more isolated as galactic islands are carried beyond each other's horizons. Dark energy is the current frontier of this ancient battle, the mysterious architect that is actively curving the stage of reality toward its final, silent shape. The ultimate geometry of the cosmos is not a matter of philosophy but of measurement. That measurement comes to us from the oldest light in existence, a fossilized whisper from the dawn of time. This is the cosmic microwave background, the fading afterglow of the Big Bang itself. When the universe was a mere 380,000 years old, it cooled enough for the first stable atoms to form, allowing light to travel freely for the very first time. That primordial flash has been stretched and cooled by 14 billion years of cosmic expansion, and it now fills all of space as a uniform, faint glow in the microwave part of the spectrum. It is the universe's baby picture, and it holds the encoded signature of its overall shape. This ancient light is not perfectly smooth. Scattered across its face are tiny, faint patches, minute variations in temperature, mere millionths of a degree warmer or colder than the average. These are the cosmic seeds, the primordial lumps and valleys in the density of the early universe. They are the gravitational blueprints for everything that would follow, the future sites of galaxies, clusters, and the vast cosmic web. By mapping the precise size and distribution of these temperature spots, cosmologists can perform a profound act of cosmic cartography. They can measure the geometry of the entire universe. Think of it like surveying the Earth. If you draw a very large triangle on a flat sheet of paper, the angles add up to 180 degrees. But if you draw that same triangle on the curved surface of a globe, the sum will be greater. The patterns in the cosmic microwave background act as the universe's own giant triangles. The most detailed maps, like those from the Planck satellite, reveal a stunning truth. The patterns of hot and cold spots match the predictions for a universe that is geometrically flat on the largest scales. This does not mean it is flat like a sheet of paper in the way we normally imagine. It means that the positive curvature induced by all the matter in the cosmos, both visible and dark, is exactly balanced by the negative, repulsive curvature driven by dark energy. The two opposing influences in the cosmic tug-of-war have, on average, cancelled each other out, leaving a stage that is, for now, remarkably flat. This fossilized light provides the most precise measurement we have of the universe's fundamental shape, a silent testament to the delicate balance between the forces that build structure and the force that pushes it all apart. That delicate balance of cosmic geometry offers a stable stage for our existence, but what if we could fold it? The equations of general relativity, the very rules that describe our curved reality, contain a hidden and spectacular possibility, a theoretical shortcut known as a wormhole. Picture the universe not as a single, continuous sheet, but as a vast, multi-layered fabric. A wormhole would be a tunnel, a cosmic passageway connecting two distant points that are otherwise separated by unimaginable gulfs of space and time. The mathematical concept is often called an Einstein-Rosen bridge, a solution to his field equations where the fabric of spacetime is folded and punctured, creating a shortcut. The classic analogy is a piece of paper, marked 2 points on opposite ends. The normal journey between them is a long line across the entire sheet. But if you fold the paper, bringing those 2 points to touch each other, you create a new, instantaneous connection. A wormhole is the three-dimensional version of that hole you could poke through the paper. It is not a tunnel through space, but a tunnel of space, a reconfiguration of geometry itself. This is not science fiction inventing fantasy. It is the language of the universe suggesting a radical architectural feature. The geometry of a wormhole involves a throat, a tunnel of warped spacetime that links two separate mouths, potentially located light years apart. An object entering one mouth could, in theory, exit the other in a heartbeat, sidestepping the long, slow journey across the cosmic terrain. Yet for all its mathematical elegance, this shortcut comes with a profound and perhaps insurmountable catch. The throat of a wormhole, according to the same equations that predict its existence, would be violently unstable. The intense curvature required would cause it to collapse into a singularity faster than the speed of light, crushing any potential traveler into oblivion before they could even take a single step. To hold this tunnel open to prevent its catastrophic pinching off, you would need a truly bizarre form of scaffolding, something physicists call exotic matter. This is not just unusual matter, it is matter that possesses negative energy density, a substance that would gravitationally repel rather than attract. Such exotic matter has never been observed in a stable, macroscopic form, though faint quantum effects hint that it might be possible in tiny amounts. Without it, the beautiful bridge collapses. So while the geometry of wormholes reveals a universe more interconnected and stranger than we ever dreamed, it also places a formidable lock on that door. For now, these cosmic shortcuts remain a breathtaking testament to the power of curved spacetime, a ghost in the machine of general relativity, waiting for a key we have not yet found. Yet even the grand geometry of wormholes rests on a smooth cosmic fabric, a landscape that seems to dissolve when we look too closely. At the very smallest scales, the universe becomes a chaotic sea. The gentle curves of spacetime predicted by general relativity are shattered by the frantic, probabilistic rules of the quantum world. Here, the smooth fabric is expected to break down into a seething, frothing foam, where tiny wormholes and baby universes blink in and out of existence over distances trillions of times smaller than an atom. This is the final, unfinished battlefield, the point where our two most successful theories of reality meet and refuse to speak to each other. On one side stands general relativity, with its beautiful description of gravity as curved geometry on cosmic stages. On the other stands quantum mechanics, which governs the frantic dance of particles with unerring accuracy. Each theory is brilliantly powerful in its own domain, yet they become mutually incomprehensible when forced into the same room. Uniting them into a single framework, a theory of quantum gravity, is the greatest unsolved problem in all of theoretical physics. This is where the tug-of-war enters its most profound and mysterious phase. The conflict is no longer just about how mass tells spacetime how to curve, but about what spacetime actually is when you examine its most fundamental ingredients. Is the smooth continuum merely an illusion, a kind of cosmic average of something far more granular? Two leading ideas offer radically different answers. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. In this view, every particle is a different note played on these microscopic strings. The properties of these particles and the forces they feel are determined by the hidden geometry of extra dimensions, dimensions curled up into shapes so small we never perceive them directly. The geometry of these compactified spaces dictates the symphony of the universe. The other major contender, loop quantum gravity, takes a more direct approach. It suggests that spacetime itself is not continuous, but is woven from a fabric of finite, discrete loops. Picture the smooth spacetime of general relativity as a calm ocean. Loop quantum gravity reveals that this ocean is actually made of individual droplets, a fine, atomic structure of space and time. In this picture, area and volume come in tiny, indivisible units, a pixelation of reality itself. The conflict between these visions is not just technical, it is philosophical. It forces us to ask what space and time truly are. Are they a fixed background stage, as Newton believed, a dynamic, curved fabric, as Einstein showed us? Or are they perhaps an emergent property, a collective behavior of countless microscopic connections, like the smooth surface of water emerging from the frantic motion of molecules? In the quantum realm, the very concepts of here and there, of before and after, may need a radical overhaul. The battle between geometry and gravity has brought us to the edge of known physics, to a frontier where the map of reality is being redrawn from its very foundations. That silent warping of time is not confined to distant clocks or black holes. It is at work right here in your pocket, correcting your path to the nearest coffee shop. Your smartphone's GPS is a perfect, everyday proof of Einstein's curved reality. The system relies on a constellation of satellites, each one carrying an incredibly precise atomic clock. These satellites orbit about 12,000 miles above the Earth, far from the deepest part of our planet's gravity well. From their higher vantage point, they experience a slightly weaker gravitational pull. Because of this, time for them flows just a little bit faster. It is a tiny difference, only about 38 millionths of a second gained each day, but it is absolutely real. There is another factor at play as well. The satellites are moving at tremendous speeds relative to the surface of the Earth, and this velocity itself causes a separate kind of time dilation, a prediction from Einstein's earlier theory of special relativity. This effect makes the satellite clocks run a little slower. It is a cosmic tug-of-war, with gravity speeding the clocks up and motion slowing them down, but the gravitational effect wins. The net result is that the clocks on the satellites gain a little over 38 microseconds every single day. This seems like an impossibly small error. What could a few millionths of a second possibly matter? For GPS, it is everything. The system works by triangulating your position based on the precise timing of signals sent from multiple satellites. These signals travel at the speed of light, which covers nearly 300,000 kilometers every single second. If the satellite clocks are running even microscopically fast, the timing data they send becomes flawed. An error of just 1 microsecond translates into a positioning mistake of over 300 meters. If the engineers did not deliberately build these relativistic corrections into the system, your phone's map would be useless. The location it shows you would drift by several miles each day, leaving you completely lost within hours. So every time you open a Maps app to navigate, you are not just using satellites. You are using satellites whose computers are continuously applying the precise equations of general relativity to stay on track. You are relying on our understanding of curved spacetime to find your way home. This is not a laboratory experiment. It is a technology used by billions, a constant, invisible reminder that the geometry of the universe is woven into the fabric of our daily lives. That dark heart in galaxy M87 finally has a face. For the first time in human history, the Event Horizon Telescope project did not just detect a black hole, it took its picture. The now iconic image shows a fiery, lopsided ring of light encircling a profound central darkness. This is not the black hole itself, for a black hole is an absence, a puncture in spacetime from which no light returns. What you are seeing is its shadow, a silhouette cast against the glowing backdrop of superheated matter spiraling into the abyss. This shadow is the ultimate expression of curved geometry. The gravitational pull is so overwhelming that it creates a sphere of no escape, the event horizon. Any light ray, any photon that ventures too close will have its path curved so violently that it is captured forever. The dark central void is not an object, it is a region of spacetime from which every possible future leads inward. The bright ring surrounding it is composed of light from the accretion disk that is being whipped around the black hole. Some of that light is bent by the intense gravity, lensed around the void in a perfect circle, illuminating the edge of the darkness itself. The precise size and shape of this shadow are not arbitrary. They are a direct geometric readout of the black hole's fundamental properties. Its diameter is dictated purely by the object's mass, a perfect circle for a non-spinning black hole. The slight asymmetry, the lopsided brightness in the ring we observed, is the signature of a ferocious spin, a drag on the fabric of spacetime itself that twists the paths of nearby light. This single image, a testament to global collaboration and exquisite precision, is more than a photograph. It is a direct visual measurement of a gravitational monster's mass and rotation, a confirmation written in fire and shadow that Einstein's geometry of curved spacetime reigns even at the very edge of reality. Even the steady spin of our own planet leaves its ghostly signature on the cosmos. A massive, rotating body does not simply sit in the fabric of spacetime. It actively stirs it. Picture a spoon slowly turning in a jar of thick honey. The honey closest to the spoon is pulled along, creating a gentle swirl around it. In much the same way, the Earth, as it spins, drags the very framework of space and time around with it. This phenomenon is called frame dragging, a subtle but profound prediction of Einstein's universe. It means that mass does not only create a static depression, a mere dimple in the cosmic fabric. Motion itself imparts a dynamic, swirling curvature, twisting the invisible threads of spacetime around the rotating object. To prove this ethereal effect existed, scientists devised one of the most precise experiments ever attempted. NASA's Gravity Probe B mission placed a satellite in a perfect polar orbit around Earth, carrying gyroscopes so perfectly spherical they were hailed as the roundest objects ever made by humans. These gyroscopes were isolated from all external forces, their spin axes pointed at a distant guide star as a fixed reference point in the cosmos. If our planet were simply a static mass, those gyroscopes would have remained locked on that star forever. But if Einstein was right, the swirling, dragged spacetime around our spinning Earth would ever so slightly tug on the gyroscopes, causing their axes to drift over time. The effect was minuscule, a drift angle equivalent to the width of a human hair seen from a quarter of a mile away. But after years of painstaking data collection, the drift was there. The results confirmed it. Space and time are not just curved, they are twisted by motion. The very void through which our planet travels is not a passive backdrop, but a dynamic fluid, stirred by the dance of every spinning star, every rotating galaxy. This swirling, dynamic fabric of spacetime might be nothing more than a magnificent illusion. The holographic principle proposes a reality so strange it defies all intuition, suggesting our tangible, three-dimensional world could be a projection from a two-dimensional surface. Think of the security hologram on your credit card. It appears to have depth and solidity, a three-dimensional image you can almost reach into. Yet all of that information is encoded on a flat, two-dimensional plastic film. The holographic principle applies this same logic to the cosmos itself. It states that all the information needed to describe everything within a given volume of space, every star, every person, every whisper of light, can be perfectly stored on its outer boundary. Our universe, with its galaxies and gravity wells, might be a cosmic hologram projected from the edges of reality, from a vast, two-dimensional surface we can never perceive. This idea did not emerge from pure philosophy. It was forced upon us by the paradoxical nature of black holes. A black hole's event horizon is a surface, a two-dimensional sphere that marks a point of no return. Yet when matter falls in, the information it carries seems to be lost forever, violating a fundamental tenet of quantum mechanics. The holographic principle resolves this by suggesting the information is not lost inside the hole, but is instead smeared and stored like a pixelated image across the entire area of the event horizon. The three-dimensional interior, with its terrifying singularity, is encoded on its two-dimensional boundary. This implies a profound and shocking connection between geometry, gravity, and information. In this view, gravity and the three-dimensional world we experience are not fundamental. They emerge from a deeper, more basic reality defined on a distant, two-dimensional surface where gravity does not exist, only quantum information dances. The entire cosmic tug-of-war we have traced, the bending of light and the slowing of time, could be the projected shadow of a flat, information-rich surface. It challenges our most basic assumptions about what is real, hinting that the geometry we feel is just a story being read to us from the edge of the universe. Our universe could be a single bubble adrift in an endless cosmic sea. The multiverse theory stretches the concept of cosmic geometry to its absolute limit, proposing that what we call reality is just one pocket of spacetime among countless others. Each of these cosmic bubbles may have inflated from its own seed event, a process known as eternal inflation. In this vast landscape, different regions of the primordial cosmos underwent rapid expansion at wildly different rates, pinching off into separate universes, each with its own unique physical properties. The very laws that govern one bubble, the strength of its forces, the number of its dimensions, and the outcome of the tug-of-war between geometry and gravity, could be completely different in the next. In one universe, gravity might be so overwhelmingly powerful that it instantly crushes all matter into black holes. In another, dark energy might be so weak that the cosmic expansion never gains momentum, leading to a swift and catastrophic collapse. The geometry within these bubbles is not fixed by a single universal law, but is instead a local and perhaps accidental outcome. The space between these bubbles, the wider cosmic landscape, could possess a geometry so alien that our concepts of distance and connection become meaningless. This vision pushes the idea of curvature to its logical extreme. The battle between the attractive pull of gravity and the repulsive push of dark energy, which in our universe results in a nearly flat geometry, might have an infinite number of different resolutions. Some bubbles may be perfectly spherical and finite, while others are open and hyperbolic, stretching into infinite emptiness. The cosmic tug-of-war we have been tracing is not a single, definitive event. It is a drama playing out on an infinite number of stages, each with its own unique script, where the fundamental constants of nature are not constants at all, but merely the local bylaws of our particular bubble. A black hole's silence is not empty. It hums with a hidden heat. For decades, physicists viewed these gravitational pits as perfect one-way streets, cosmic traps from which nothing, not even information, could ever return. This simplicity, however, created a deep conflict with one of science's most cherished laws, the second law of thermodynamics. This law states that the total disorder or entropy of the universe must always increase. If you could throw a box of hot, chaotic gas into a black hole, you would be erasing that entropy from the universe, seemingly making the overall disorder of the cosmos decrease. This was the black hole information paradox, a glaring contradiction that suggested our fundamental laws of physics broke down at the event horizon. A young physicist named Jacob Bekenstein made a radical proposal. What if the black hole itself possessed entropy? What if its terrifying darkness was not a void of zero disorder, but actually represented the maximum possible entropy any region of space could contain? He boldly suggested that a black hole's entropy was not proportional to its volume, as you might expect for a three-dimensional object, but to the surface area of its event horizon. The larger the black hole's shadow, the greater its hidden disorder. This idea was initially met with skepticism. If a black hole has entropy, then by the rigid rules of thermodynamics, it must also have a temperature. And any object with a temperature must radiate energy, but nothing can escape a black hole, or so everyone thought. Then Stephen Hawking performed the calculation. Applying quantum theory to the curved space just outside the event horizon, he found that black holes are not completely black. They emit a faint, whisper-thin glow of radiation, now known as Hawking radiation. This radiation carries away energy, causing the black hole to slowly, over eons, evaporate. Hawking had confirmed Bekenstein's audacious insight. The entropy of a black hole is precisely 1/4 of the area of its event horizon, measured in fundamental units called Planck areas. This result, the Bekenstein-Hawking formula, is deceptively simple, yet its implications are earth-shattering. It forges an unbreakable link between the three great pillars of physics: gravity, thermodynamics, and quantum mechanics. Gravity, described by the curved geometry of the event horizon's area, is fundamentally intertwined with heat and disorder. This connection reveals a universe where the most important information about a volume of space, its total entropy and information content, is not stored within its depth, but is somehow painted onto its two-dimensional boundary. The curvature of space is no longer just a geometric stage for matter to play upon. It is a dynamic, thermal canvas. The warped surface of a black hole encodes the history of everything that ever fell in, a cosmic ledger written not in the void but on the veil that shrouds it. Those black hole mergers, detected as faint chirps by LIGO, were deciphered using a digital crystal ball. The mathematics of curved spacetime is so complex that when two black holes spiral together, no single equation can chart their violent embrace. To understand the chirp, physicists had to build a virtual universe inside a supercomputer, a discipline known as numerical relativity. They begin by creating a computational grid, a digital mesh that represents a chunk of spacetime. Into this grid, they program Einstein's fiendishly difficult field equations, which describe how mass and energy dictate geometry. The simulation then sets two virtual black holes in motion, and the supercomputer calculates, nanosecond by nanosecond, how their immense masses warp the grid around them. It solves for how the fabric stretches, twists, and finally ruptures as the event horizons merge into one. These are not simple animations, they are solutions, the only way to see the invisible physics behind the gravitational waves we detect. The resulting visualizations are breathtaking. They show spacetime not as a static sheet, but as a swirling, turbulent ocean. You see the black holes, represented by dark voids, dragging the very grid lines of space into a frenzied whirlpool. As they approach the moment of merger, the grid itself is violently shaken, sending out ripples that are the digital counterpart to the waves LIGO hears. After the merger, the new, larger black hole wobbles like a struck bell, its surface oscillating as it settles into a calm, perfect sphere, the ringing spacetime calming into a new, stable curvature. This is how a theoretical chirp is given a visual story. Without these massive simulations, the signals from LIGO would just be curious squiggles on a graph. Numerical relativity turns abstract mathematics into a predictive, visual science, allowing us to witness the most dramatic choreography in the cosmos, the dance of geometry and gravity in stunning, simulated detail. This delicate flatness is not merely an interesting fact about the cosmos, it is a prerequisite for our existence. The balance is so precise it defies belief. If the positive curvature from all the matter in the universe had been just slightly stronger, the cosmic fabric would have curled back on itself long ago, triggering a catastrophic big crunch that would have snuffed out any possibility of life before it even began. Conversely, if the repulsive curvature from dark energy had dominated even a fraction more, the universe would have flown apart with such violence that matter could never have clumped together to form the first stars and galaxies. We exist in a breathtakingly narrow window between these two oblivions, a razor's edge of geometric stability. This stunning observation leads us directly to a profound and humbling question known as the Anthropic Principle. It suggests that the universe we measure has the properties it does, including its nearly perfect flatness, because these are the only properties compatible with the existence of conscious beings who can measure it. In a cosmos with wildly different geometry, there would be no one to ask why the geometry is so strange. The tug-of-war between gravity and dark energy, then, is not just a physical battle. It is the foundational drama that set the stage for us. Is this perfect balance a cosmic coincidence of unimaginable luck, a 1 in a trillion shot? Or is it a necessary condition, a logical outcome of a deeper law we have yet to uncover? The flat geometry we observe is not just a feature of our universe, it is an invitation to ponder our place within it, connecting the vast architecture of spacetime directly to the simple fact that we are here to see it. A new generation of ears is preparing to listen to the universe. The Laser Interferometer Space Antenna, or LISA, will not be built on the ground, but will instead consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart. This colossal instrument, floating in the serene quiet of space, is designed to hear the deepest, lowest notes in the cosmic symphony, frequencies far below what terrestrial detectors like LIGO can perceive. These low rumbles are the domain of the true giants, the supermassive black holes that lurk at the hearts of galaxies. When 2 galaxies collide, their central black holes, each weighing billions of times the mass of our Sun, will eventually spiral together. This is not the sharp chirp of stellar mass black holes, but a long, rising crescendo, a gravitational bass note that could last for months or even years as these monsters circle each other. LISA will capture this entire song, from the first faint hum to the final, cataclysmic merger that shakes the very foundations of spacetime. It will allow us to trace the dance of geometry on its grandest scale, mapping the warped space around these incomprehensible objects with a precision we can only dream of today. Beyond these galactic events, LISA might even detect the faintest whisper of all, the gravitational wave background, a remnant hum from the universe's violent birth. This would be the ultimate fossil, a direct signal from the moment of inflation, when the cosmos itself was a frothing, expanding quantum foam. This new window reveals a universe that is fundamentally dynamic, where the curvature of spacetime is not a static landscape but a constantly vibrating, ringing entity. By combining these gravitational wave signals with observations from light-based telescopes, we enter the era of multi-messenger astronomy. It is like suddenly gaining a new sense. Before, we could only see the universe. Now we can feel its vibrations. When a neutron-star merger sends out both a flash of gamma rays and a ripple in spacetime, we get a stereo view of the event. The light shows us the material aftermath, the glowing debris where heavy elements like gold are forged. The gravitational waves carry the pure, unadulterated story of the geometry, the precise choreography of the masses as they spiraled and merged. Together, they tell a complete story, revealing not just what happened, but how the fabric of reality itself behaved under extreme stress. This is not merely an upgrade to our instruments, it is a fundamental expansion of our perception, allowing us to witness the hidden symphonies of a curved cosmos. Your own mind is the most powerful observatory ever built. Long before billion-dollar telescopes or gravitational wave detectors, Einstein charted the cosmos from his armchair, using thought experiments as his instruments. These are not mere daydreams, but rigorous mental exercises that follow the rules of physics to their logical and often startling conclusions. One of his most profound begins with a simple, windowless spaceship. Picture yourself inside, floating in the deep void, completely weightless. Suddenly, you feel a firm pressure on your feet, as if the floor is pushing up against you. You can stand, walk, and drop a pen that falls straight to the ground. From your perspective inside this sealed chamber, the sensation is absolutely identical to standing right here on Earth. The ship is accelerating through empty space at a steady 1g, the same acceleration you feel from our planet's gravity. This is the equivalence principle in action, the master key that equates gravity with acceleration. Now take the experiment one step further. Imagine you shine a laser beam horizontally across the width of the ship. The light, as always, travels in a straight line. But while that beam is in flight, the entire ship is continuously accelerating upward. By the time the light reaches the far wall, the ship has moved up. From your point of view inside the accelerating box, the point where the laser hits the wall will be slightly lower than the point where it started. The beam will appear to have curved downward in a graceful arc. This is not an optical illusion, it is the direct result of your own accelerated motion. And here is the revolutionary leap. If acceleration can bend light, and acceleration is fundamentally equivalent to gravity, then gravity itself must also bend the path of light. With nothing more than the power of reasoned imagination, you have just deduced a core prediction of general relativity. You have seen, in your mind's eye, that a beam of starlight must curve as it passes through the sun's gravitational field. These thought experiments are not just historical curiosities. They are a toolkit for your own understanding, empowering you to bypass complex mathematics and use pure logic to visualize the invisible architecture of the cosmos. Our journey across this curved reality has reshaped our very vision of the cosmos. We began on the flat plains of Euclid's geometry, a world of perfect lines and predictable angles, and we have traveled all the way to the warped heart of black holes and felt the ripples of colliding spacetime. This grand tug-of-war between geometry and gravity is not some distant, abstract conflict. It is the fundamental engine of our universe, the hidden choreographer behind Mercury's restless wobble, and the silent force that keeps your phone's map from leading you astray. The cosmos is not a static stage where matter simply moves. It is a dynamic, living fabric where every star and every planet actively sculpts the geometry of spacetime, and that curved geometry, in turn, dictates the path of every falling apple and every beam of starlight. As Carl Sagan so beautifully reminded us, somewhere, something incredible is waiting to be known. Let this visual quest be your starting point. The next time you look up at the night sky, you are not just seeing points of light. You are gazing upon a landscape of invisible hills and valleys, a cosmic fabric bending under the weight of worlds. We would love to hear what part of this curved reality amazes you the most. Share your thoughts in the comments below.